Join SMPTE for a change.
Hello, everybody. Welcome to today's SMPTE Education webcast. Yeah, I'm looking very much forward to the topic today. The topic is actually going to be from volumetric video to realistic avatars, and our speakers today are Anna Hilsman and Peter Eisert. Views and opinions expressed during this webcast are those of the presenters and not necessarily those of SMPTE or SMPTE members. This webcast is presented for informational purposes only, and any reference to a specific company, product, or service is not a recommendation, endorsement, or promotion by SMPTE. So now I would like to invite our speakers, Peter and Anna, to come on screen. And they are going to be the folks that you came to see anyway. So Anna and Peter, if you would unmute your microphones, I shall turn off my camera and turn the floor over to you.
Yeah, thank you very much. So I am Anna Hilsman and I'm here with Peter Eisert. And before I come to a short introduction about us, let us shortly have a short look at the title, which is From Volumetric Video to Realistic Avatars. So volumetric video is basically a three-dimensional video that you can view from arbitrary viewpoints, for example, in VR environment. And I will explain to you in detail what this is, but it's basically a passive medium, which we can enjoy and watch passively, but it's not interactive. An avatar is basically it means a digital representation of a person in the internet and social media or in a virtual environment. And usually we think of graphical representations, but not of realistic, authentic representations of a human being. And this is actually our case. So we would like to create realistic, authentic digital representations of virtual humans. So this works. So as I said, I'm Anna Hilsman and with me is Peter Eisert. We are heading the Vision and Imaging Technologies department together at Fraunhofer HHI and also the Computer Vision and Graphics group within this department. In the department, we develop technologies in the field of video capturing, video analysis and display. And as a whole, as a department, we cover the whole video processing chain, from capturing, analyzing visual data, over modeling into digital representations, depending on the application, up to final visualization, as well as human-machine interaction. And we develop solutions for immersive media, as well as virtual and extended reality for a very broad range of applications for multimedia, industry, agriculture, medical technology, or security. And in all these applications, immersive media, as well as virtual and extended reality, have gained more and more interest. And within these applications, the digital modeling of humans holds enormous potential for development of innovative products and applications, as human models can be used as very intuitive interfaces. So we have listed some applications on the next slides, which we are currently working on, but there are more applications that you could think of. So for example, for virtual teaching or employee and communication training. So we have one project which is called VoloProf, where we are working on omnipresent learning in a virtual environment, and where we aim at creating a very realistic digital representation of an existing professor, which the students then can meet in a virtual environment. Entertainment is, of course, an application, digital storytelling, changing pre-captured data and in order to change what has been captured, for example, for filming or gaming industry. immersive communication has gained a lot of interest, especially in the past 3 years, and we are currently actually working on this topic in 3 projects. Then digital sign language specialist is actually one problem because, in order to have deaf people, give them the opportunity to enjoy digital media, they need a digital sign language specialist, and there are not so many. So it would be very good to have realistic avatars that do this job for them. And then, of course, virtual assistants are gaining more and more interest, in many applications. So the photorealistic modeling and rendering of virtual humans is extremely important and challenging, as human models can be used as intuitive interfaces, as I said, and human body and faces are very complex, but also especially as the human is very sensitive to looking at other humans. And in VR environment, not only realism plays an important role, but also interactivity. And that was not intended. And ultimate goals when creating digital humans are realism as a technical description of visual quality, authenticity, then conveying the feeling of true virtual presence, and also the feeling of connectedness. So on the one hand, we have the realism, and on the other hand, we have the interactivity. And it's very difficult to create highly realistic looking virtual humans that are also interactive. And directly connected to the term realism or photorealism is the so-called uncanny valley. So the uncanny valley is a phenomenon that digital figures gain acceptance with increasing photorealism, but there is a sudden drop in the acceptance with increased photorealism of the digital figures before the acceptance again rises for real images and videos. So in fact, this is probably not a one-dimensional function, and it's a very simplistic illustration here, but essentially we would like to understand this function, which is probably highly dimensional, and we would like to understand it in order to create highly realistic people and virtual humans and not fall into this valley. So this is just the motivation. We don't have an answer for this now, but this is also one topic we are working on. So usually when animation is required or interactive environments need virtual humans where the user can interact with, usually computer graphics models are used. So computer graphics models are highly interactive and can be animated. So the body can usually be animated by a skeleton. So the computer graphics models is a vertex mesh, and you have a surface, and usually it's rigged. That means you have a skeleton underlying, and each vertex has a rule how to behave and how to move depending on the skeleton motion. And similarly for the face, where you have like blend shapes that can be used to animate the face. So these graphical models are highly interactive and modifications are possible, but it's really difficult to gain real photorealism. So this is really expensive. You have to put in a lot of manual effort, and it's especially for real-time applications, it's very difficult to gain real photorealism for interactive avatars. On the other hand, we have images, videos, volumetric video, and I will explain what this is later. So real captured data, which is highly detailed and realistic, but usually no modification is possible. So for example, volumetric video, you have a 3-dimensional video, which you can view from arbitrary viewpoints in a virtual environment, which is really realistic as soon as the user is in a passive role. As soon as the user wants to interact with the virtual human and the virtual human does not react to the user, the immersion is lost. So one goal is to combine the interactivity of computer graphics models with the realism of real captured data. And I have listed images and videos and volumetric video here. So the first question is, what is volumetric video? So volumetric video is essentially a 3-dimensional video, a 3D reconstruction of a human performing some motion over time. So what you see here on the figures is our first capture studio, which we have in our institute. It's a 360-degree volumetric video capture studio, where we have placed cameras in 360 degrees around a person performing some motion. And we can now reconstruct a three-dimensional representation, a mesh, a surface mesh, of this human performing this motion for each time instance. And what you then get is yes, that works. And what you then get is a 3D reconstruction per time instance with colors and the texture attached. So what you see here is on the left-hand side, you see the geometry and you see this flickering. This just shows that we have independent reconstructions per time instance. And on the right-hand side, you see the textured mesh. And as I said, you can now put this into a virtual environment and view this from arbitrary viewpoints, but you cannot directly interact with this data. So this is one example for virtual humans represented as volumetric video, which our spin-off company Volocap created together with the German news Tagesschau. So the goal is here to bring the anchor woman into the living room or wherever the user is and watch the news from 360 degrees. But now imagine you could interact with the anchor woman. So this starts with just establishing eye contact between her and the user, or changing the mouth when translated to another language, or direct interaction with the anchor woman. So the immersion is kept as long as the user or the viewer is in a passive role, but it breaks as soon as he tries to interact with the virtual human and he or she does not react. So the question is now, how can we combine interactivity and realism and create highly interactive digital representations that still have the realism that we have in volumetric video? So the question is, can we train, for example, an artificial intelligence or a neural network that can learn from these highly accurate and highly realistic input data that we have from the volumetric video in order to synthesize new poses, new motions, given some input like a novel pose, a novel viewpoint, or some new facial expression? So now we have to step back one step in order to answer this question, how to do that. So usually when animation is required, as I said, we use usually computer graphics models. So these models are meshed surfaces, usually rigged with a skeleton, and they carry semantic information, which means each vertex has a semantic information and knows how to move when the skeleton is moved. So we have some animation rules and can change the pose of the person. And usually these models can be adapted by altering some weights of or parameters of the models can be adapted to a given body shape, which we have, for example, captured with the volumetric video. So computer graphics models carry semantic information and they are animatable through a skeleton. And there are several models in the literature, but currently mostly used is the so-called simple model, which has some variations with hands and also expressive faces. But just we use the simple model for simplicity in the following slides. So this is an animatable parametric model that can be adapted to the shape of a person and which can be animated. So usually what up to a few years ago, what you would have been doing when creating a digital avatar from volumetrically captured humans would be to adapt such a model in the shape and the pose to all the frames in order to fit the model in shape to the captured person, and then throw away all the captured data and use this adapted model as an avatar. Then, however, you lose all the fine details that you have captured with the volumetric data. So this is why we followed at the beginning a different approach. We fitted the model to the captured data and then did not use the model as a new avatar, but we used this to drive an animation of the volumetric video. So we have established correspondences between the model and the volumetric video, and then can just transfer the motion of the model to the volumetric video frame. So what we see here on the left-hand side is a video of a volumetric video sequence where a basketball player explains how to play basketball. And you can watch this in VR, and it's highly realistic when you face him from the front. But as soon as you step aside, the immersion is lost because he speaks in the same direction as before. And on the right-hand side, you see the same sequence where we animated the head pose using this fitted simple model, which we fitted to the original data. So, but the problem is that this kind of animation has some limitations. So it's possible for the head rotation. It's also possible for some degree of motion. But if you try to animate different poses than those that you have captured, you will get some artifacts. So another question is, so with recent developments in AI and neural networks and also generative models that can be trained to generate new content, would be one question: can we train a neural network to learn how the volumetric video data behaves so that it can generate new poses, new motions given an input? And the question there is what is a good encoding if we want to put in the volumetric video data into this neural network? So if we would train a neural network on the original data, we would the network would have to learn also the human shape and how a human moves. But this is actually some a priori knowledge that we have, so we can directly use the model that we have fitted to the data in order to limit our search space for the neural network. And also the SMPL model, which we have fitted to each frame of the volumetric data, yields pose labeling. So we have a pose label for each time instance in the volumetric video frame. And with pose labeling, I mean we have a skeleton representation which represents the pose of the human in this frame, and the labeling would then be just a vector of all the joint angles. And it also gives us some kind of parameterization space where we can parameterize the appearance and also the geometric differences between the frames. So these videos show the fitted SMPL model to the original data. So in blue, you see the original volumetric video frames. So this is basically a mesh without the texture. And the model is depicted here in green or red, and the colors actually encode the differences, the differences in geometry between the model and the captured data. So you see, for example, for the man, the differences at the chest are very high because he's wearing a loose jacket. And this is actually the answer to the encoding. So we can encode the geometry differences between the model and the actual data by translating the differences between the model and the captured data into a texture map or a displacement map, so that we can train a model based on these maps. So what we can do now, we can encode the appearance differences, so all the fine details that change according to the pose, so fine wrinkles, shading that appear at the clothing. We can encode this in the texture map of this model, of this SMPL model. And this is the advantage, that the texture space of the SMPL model is consistent, temporally consistent, in contrast to the actual captured volumetric video frames. And the geometry can now be encoded as some kind of displacement map, so a displacement for each surface point between the model and the captured data. And we can encode this in a map similar to this texture space, so that we can train on images rather than on geometric representations. So the idea is to train generative models for these maps rather than the full geometry. And we also weight the two maps based on the confidence and the visibility that have been calculated based on, for example, how many cameras have seen which surface point, or how occluded a point is, and so on. So what we do now is we train a network. We have the volumetric video frame. We have the SMPL model, which is consistent, which has a consistent topology. We have this one fitted to the volumetric video data. We project the texture from the volumetric video frame to the model. So we have a consistent texture map over time. And we calculate a displacement map between the model and the volumetric video frame, and encode this also in a texture map in the same space as the texture map, which is the SMPL texture map. So we can now put this into a encoder network and train it such that it can synthesize the texture as well as the displacement map, so that new poses can be generated. So we have this underlying SMPL model, which we can animate to a new pose. So we first fit it to the shape, then we can animate it to a new pose, and then we can synthesize a texture map and a displacement map, which add all the fine details in the appearance and the geometry. So this is one result. Right now on the right-hand side, the volumetric video, and on the other hand side, now it turns. On the other side, the synthesized model. So this is a secret that has not been used for training. It's just for the comparison. So yeah, on the right-hand side, the ground truth, and on the left-hand side, the synthesized versions. And you see on the where you see the meshes, that the left-hand side has this consistent topology of the SMPL model. And you see that also here for the synthesized version, also the fine shading changes when she moves her arms. So before we come to the facial animations, and when I will give the word to Peter, I would like to show you some new approaches that have gained a lot of interest in the computer graphics community. So in recent years, implicit representations, especially neural radiance fields, have gained a lot of interest in computer graphics. And these neural radiance fields, shortly NURFs, are basically a continuous volumetric scene function, which is learned from a sparse set of input views. So it's a continuous function learned by a multi-layer perceptron, where you get the color and some kind of alpha map or opacity given viewpoint and viewing direction. And there are currently also new versions like Instant NGP, for example, for fast training. So this is no explicit representation with a mesh and a texture, but this is basically a function represented as this MLP, where you get the color of each pixel based on this volumetric rendering from the scene function. So this is one example where we trained this NURF for a static frame of our volumetric video capturing. And what we are currently working on, which is just the current state of research, is we would like to build something like this implicit representation, like this NURF, also for different poses. So instead of creating or learning a continuous function for viewpoint rendering, we are currently working on a method that can do this also post-dependently. So we are training an MLP that synthesizes a human for a given skeleton pose based on viewpoint, view direction, as well as pose. And this is actually the current state of the results. There are a lot of challenges because there is ambiguous appearance, alignment errors of the model, and so on. But as these implicit representations are emerging, we think that this is actually the future for the representation, also for virtual humans. This is where I hand over to Peter or take your questions.
Hello, thank you. I love this stuff. I love it. Peter, I have a couple of questions, but before I ask my questions, I would like to remind our guests that your questions are more important than mine. And so please cue your questions at any time, but now. And just type in, I have an oral question if you'd like to speak to Anna or Peter. But my first question, and I always say I'm not an engineer. I understand a little bit about technology, but what about the process of de-aging actors? Which model might be used or is used to accomplish this?
For aging?
Yeah, de-aging.
De-aging. Okay.
I recently read an article that Harrison Ford is going to do another Indiana Jones movie, and in it he will be de-aged.
All right. I mean, this could also be done with some kind of trained AI model where you put in images of people of different ages, and maybe you can train a translative function which translates one image to another and can also translate an image from a younger person to an older person. But actually, I think that in these Hollywood movies, this is a lot of manual work.
Yes. Okay.
Maybe just to add on that, so we a couple of years ago we had a project where we actually worked a bit on this problem. So we developed tools for, in this case, aging, not de-aging, for post-production companies. And together with these companies, we built tools where you could add age effects. And then they were tracked over time in order to change the appearance of the actor. So this was a pure video-based approach, but based on deformable tracking. But it was a nice tool for aging or de-aging. We both tried both of them.
Great, thank you. We do have a question in the queue from our good friend Hans, the most recent past president of SMPTE. And Hans asks, can this be done in real time?
The question is what this refers to, but yes, in general, yes. So especially the question is the input currently also so especially for this for the body animation, because as I said, we are currently working on this post-dependent representations. The question is where the pose comes from. You have to capture it. But Peter will shortly show some examples for facial animation, where we have actually also created some real-time applications where we can directly animate from text or speech. And we are also currently working on speech-driven gesture synthesis, where we synthesize skeletal motion based on speech, which can then be transferred to the model in real time.
Okay. And I promise this is my final question for this segment. How detailed can these models become, be produced? Is there a resolution limit today for them?
Yeah, so currently the resolution is, so we capture in this volumetric studios, there the resolution is limited by the cameras and also the resolution of the mesh that we capture. In theory, these implicit representations are independent from resolution, because what the MLP does, it learns a continuous function. So in theory, these implicit representations are independent of a resolution. But of course, you still have to render them on a device which has a resolution.
We do have one more question from an anonymous attendee. And let's see if it's actually two questions. Are you using normal TOF cell phone to capture and construct the 3D model or a special device? And how is the neural network training progressing?
Okay, these are two very different questions.
Yes.
The first is we are actually capturing in our studio. So we are using the volumetric studio that I showed in order to get this highly realistic data. You could also capture actually with or use other capturing devices, and then you get low dimensional models which you can train your network with. But in order to get all these fine details, we need like we need a lot of cameras with a high resolution.
Okay. And
the second question was on the training of the network, how it's progressing.
Yes. How is the neural network training progressing?
Oh, depends on which neural network. I mean, probably the question is on the synthesis of this texture and the displacement map.
Mm-hmm.
I think that so it has Sorry, I probably lost the connection, but I will start again. So for the training of this texture map and this displacement map, this representation or this parameterization over the SMPL model helps to limit the search space. So the training is converging.
Okay, great.
Just for the nerves, there has also been a lot of progress. So, maybe 1 year ago, then training took a couple of days, and now, due to some enhanced algorithms, you can do that in seconds. So there is also from different techniques also progress in training.
Okay, so the question was on the time of the training. Okay.
We have one more question. I promise this will be, unless another one pops up when I say that. And it's an interesting question from Brad. Can this also be done for animals or other creatures, thus offering a wider range of characters for a production?
Other characters than humans?
Yes. Animals.
Yeah. In theory, we could also try to capture animals. The question is, so we on the one hand we use this real captured data that we could probably reconstruct any object, that is captured in the studio. But what we are currently referring on is this simple model, which has been trained on a lot of captured human shapes. Of course, you could also train something like this also on animal shapes, for example, but this is currently not available.
Right, so it's not within the scope of the research that you're doing.
Yeah, sure. Because it's actually, I think that, it's a practical problem how to capture animals and tell them what motions to do in order to get a good statistical model.
Yes, I have a cat that you could not. No matter what you do. Okay, that is the last question in the queue. Thank you very much. I shall turn off my camera, and Peter, I think you are next.
Okay, thanks. Then also welcome from my side. So Anna has told you a bit how we work on synthesizing human bodies, and I will now take over to show you some results for synthesizing faces. And there we use similar techniques, although things are a bit different because we don't have the skeleton, we have other parameters to animate with, and we have a lot of deformable surface motion, which is also just shown here. If you have an actor acting in front of a camera, you have a lot of facial expression and motion in the face, which you have to deal with. But here we follow a similar approach. we want to rely on very rough and simple models that describe the dominant shapes of a human, and then add more details which are actually learned. So what you can see here is on the left side, the captured video of an actress, and we track her in 3 dimensions such that we get a stable head position, and from that we extract texture maps, which are also shown here in the middle, and a very rough geometry. And the idea is to have the rough geometry in order to manipulate and to edit the facial expressions, but to reproduce all the fine details that are in a face, which are very difficult to model with 3D models, to model them just by textures which we overlay on top of the model. And on the right, you can see the final rendering, and you see the person moving and acting as in the original video. And now we want to learn such a representation such that we can also do animation of new content. And for that, we use captured sequences. So let's say 1 minute of a person speaking, and we have all the texture map extracted and the models with some simple blend shapes extracted. And you can see that the shape model does not even have a mouth opening. It's just a closed mouth, closed eyes, and we overlay just the texture on top of that. But we can represent facial expressions with that approach, and we use an autoencoder in order to learn the representation of shape and texture. And we have, after the encoder, we have a very small latent vector, which consists of 1024 values, which represent shape and appearance of the face. And from that, we can then learn how to synthesize the geometry again and the facial expression by means of the texture maps. And with that, we can now reproduce the original shape. And here, this is shown as an animation. On the right, you can see the original video captured. From that, we have extracted this latent description, which is just a vector of 1000 values per video frame. And from that, we can synthesize the appearance. And you can see in the middle the model, which is our rough model, but it shows all the teeth and the tongues and the eyes, although we have not modeled them. And this is just due to the fact that we have just extracted the texture information on top of the model. The problem with that approach is that it's not perfect. So we have fine details in the mouth region, but we lack some details. For instance, the ears are not completely modeled. The hairs are not correct. So we use AI in order to improve these artifacts or these mismatches between the original image and the rendered model by a neural network. So we train again an autoencoder unit type structure, which can takes an imperfect model as input, and from that create a better output. And better output means we correct the image by estimating a corrected image. We also estimate several alpha masks in order to composite all these elements. And with that, we can now synthesize the model and remove all these artifacts. And here you can see at least some static examples. So these are 2 pairs of faces where the left part is actually created from our rough 3D model. And you can see here the crude outline, and also the mouth is closed and not open. And on the right hand, you can see the improved version, and just with correcting all these artifacts. So we learn the network just to produce a realistic appearance of the face. We can get rid of many of these artifacts. So suddenly the mouth is open, so we can look through the mouth, but also the outline of the hair, and even some view-dependent hair is visible by this approach. So this is static, but here you have an animation of the same sequence, and here you can see, on the second image from the left, you see our rendering with our 3D model, which shows these rough silhouettes, and from that we synthesize a corrective image, which is shown on the right, and by compositing all these images with the alpha maps and compositing channels, we get the final rendering, which is shown on the right. And here we have now, although we have a very rough model, we have a realistic outline and detailed model of a human face that we can now animate for different kind of applications. So I mentioned that we create, besides the improvements, which you here again see for another video sequence, left again the rendering, then the middle is the corrected view using our neural rendering techniques, which adds all the nice silhouette effects. And on the right, you can see that we can also create these alpha masks, which now enables us to embed these representation also in other virtual scenes, which we need, since this technology, or the last step, the neural rendering step, is a 2D approach. And since we want to embed that into 3D scenes, we also need some kind of alpha channel information. And this works quite well. We have compared that with other approaches. And here you can see on the right, our mask and other approaches, they just have not such a clear mask, which makes it a bit more difficult to composite such elements into new scenes. And here you can also see a visual comparison between different approaches. They all target the same visualization of facial animation using such kind of neural rendering techniques. On the right, you see the original video. That is the ground truth that we want to achieve. Besides that, you can see our approach, which looks very close to the original video, and then 3 other very recent approaches that we compared with. And here you see they all perform quite well, but they have different kind of artifacts. And we wanted to know a bit about these artifacts and how people find the quality and the realism of these approaches. So we conducted a user study with about 70 non-expert participants, and we played several videos using different techniques for them. And we asked them to judge the quality on a scale between 1 and 5, with 5 being the best. And if you look here at the table, here on the right, you see the ground truth. And of course, the original video has a very high quality with almost 5 as a result. But our result is also very close, with an average score of 4. So people actually somehow like these approaches. So 75% say that these kind of representations show a high or very high quality. And compared to these other approaches, we have still a gap between this the judged quality. So these approaches seem to be quite accurate. We can now do animation with these representations, but I mentioned that we animate from a latent vector, and this has not really a semantic meaning. So we have our autoencoder that can reproduce original sequences, but that's not what we want to do. We want to animate. So we throw away the encoder and just use the decoder. So we input the latent vector and we get a 3D model and the corresponding texture out of that. And that's nice, But there are some problems because these animation parameters, they not have really a semantic meaning. They are just learned from an neural network, but without any semantic meaning that the user can actually use as input. So we need some kind of mapping of meaningful input parameters to our latent vector representation, and we do that by using neural network that learn a mapping between different types of input, text, speech signals, but also videos of acting persons, which transfer the motion, the audio signal, or the text to a representation in our animation. And in order to have a better control, we separated the parameters in the face in different regions. So we have one latent representation for eye movements and another latent representation for the region around the mouth. And then we have another set of parameters for global head motion. And with that, we want to animate the face. And one very simple approach as input interface is to do that from text input. And if we want to animate from text and make a virtual character speak a given text, for instance, that comes out of ChatGPT or any other text generation assistant, we just map the text sequence into a sequence of Y-seams, which are the corresponding visual appearances corresponding to phonemes. And then we have a mapping network that maps the sequence of Y-seams to an animation sequence. And if you want to animate from a speech signal, so if you want to take a microphone, say something, and then create the corresponding animation from that, we then use speech recognition and audio alignment in order to create also a visual sequence that we can now use as driver for our animation. And of course, we also want to make it more realistic, also to generate lip movements, eye movements, and global head movements in order to not have a static representation of the face. One problem that we have from these Y-seam sequences is that we usually don't have a one-to-one correspondence. So if you have or speak a certain phoneme or show a certain Y-seam, the mouth shape could depend on the local context of what you're saying. And here you see 4 different visual appearances for the same spoken letter T. So it depends a lot on the context. So we have to learn somehow the relation and the flow of the speech in order to have the right pronunciation for the lip movements. And we do that by learning how a realistic animation is conducted by training a network on the original data. So we have the original video sequences, we have a captured speech signal, and we can derive the Y-seam sequences and then use that in order to learn mapping networks. And we use as input our Y-seam sequence. Then we have an animation network that translates these textual descriptions into a frame-wise representation of animation parameters. And this animation network has learned all the dynamics of lip movements and all the sequences of different phonemes, how they are converted into lip movements. This is true for one person, but even a single person can speak in different ways and different, I have to go back. So in different ways and different emotion and style. So we somehow have also to control style. And we do that by adding a style encoder that is learned unsupervised in an unsupervised manner from different recordings of an actor or actress. And at the end, we have some kind of sliders and style parameters where someone can edit the style and can create a more expressive or a more sad or other types of styles representation of the same speech. And then we also add some kind of animation priors in order to make the motion more realistic. And this is especially important for global head motion because this is less correlated to individual phonemes or voicemes in the speech. So what we do is we take the video sequences and then we learn the dynamics of human speech, and these representation of dynamics are then represented by a neural network that we add as a prior information in our animation pipeline in order to just reproduce realistically moving faces. And here you can see on the left, if we avoid all these prior information, we get some kind of jittering output of the face. But if we add this learned dynamic representation, we can create something that looks much more fluent and realistically. And here you can see two examples of speech-driven animation. And can we play these videos one after the other? Joel? Could you please start?
I'm here.
Yeah,
yes.
Could you please start the left video and then the right video? Because
I tell you a story about a girl. She lives in a big flat in Berlin. This girl is 5 years old.
And then the right video.
Paying great attention to the press work or actual process of printing, so far as fine printing is concerned, though paper did not get to its worst till about 1840.
Yeah, so these are just two examples where we now use the audio signal in order to animate the faces, and these were just taken audio signals from a public database. So this is a very easy way to represent animation, and if we can play that video as well, here we have the same animation but rendered in different styles. So you see it on a 2D plane, the same animation but with different kind of style parameters. So we have some artistic tools where we can just edit the way how these animations are actually played. And we have also asked again, so now it's playing. Here you see that you see the same animation, the same spoken text, but different variations. And this is some other user input that you can now control in order to have more or less expressive animations. Yeah, and we have also asked people how they judge quality. Again, same 70 participants, and we asked about visual quality, about the synchronization of audio and visual signal, but also on the realism of the facial expressions. And again, compared to ground truth, we got very good results. Here you can see also the visual appearance compared to 3 other very recent approaches that do all text and speech driven facial animation. And here we have very nice results with high visual quality. So now we have a representation that we can control. We can animate it from different kind of sources. We get a quite high visual quality, but sometimes this is not sufficient. But you can also try to work with other approaches. And at the end of our talk, I would just like to give you some outlook on what other techniques that are around that also use AI for visualizing faces and humans. And you have all heard about deep fakes, where the idea is to replace an identity by someone else, which is often used in a context, in a bad context of faking identities, of doing, showing fake news or other, not very positive things, but you can use these techniques also in animation of faces. We are also working on deep fakes, in particular for novel kind of detection methods. We want to detect whether a video is genuine or faked, but we also have to create different kind of training data in order to have a good fake detector. And here you can see that these fakes really pose a threat or can create realistic images, depending on how you see that. And here in the middle, we have our original video, and on the left, we have replaced the left person, and on the right, we have replaced the right person in the image. And you can also watch that as a video. And here again, we have replaced the right person in the video, and you can see that it's really hard to see if there is some modification going on. So you have high visual quality. On the other hand, the ways on how you animate such videos is more restricted. Here you have basically a driving video that determines the facial expression of the target person. But it's another way of representing faces and animating them. And here these deepfakes that have made very high progress in terms of quality. Some years ago, they were very easy to spot any artifacts, but nowadays they are getting better and better, and it's much more difficult to judge whether an image or a video is genuine or faked. And this is further increased also by recent developments, for instance, in diffusion models, which are, for instance, very well known for systems like DALL-E. And this is another method that can replace GANs for synthesizing faces or other images with very high quality. And here you can see the additional benefit they produce. So if we use our standard auto-encoder techniques, which is shown here in the middle, we get still very high quality, but if we zoom in, we see some blurred results in the eyes. But using these diffusion techniques, we can further improve the quality and show even small details. And this can be used to reproduce very realistic animations of faces, but with the caveat that they are less controllable compared to our 3D representation of faces with hybrid textures. But in order to end our talk, I want to come back to Anna's initial question about realism. So we have spoken a lot on photorealistic representation of human that are interactive. We want to produce realistic results, but the question remains, what is actually realistic? And Anna has shown you this nice diagram about the uncanny valley. And this is what we actually have as a final goal, because human perception is at the end what matters most. So if the human doesn't accept the results or is annoyed or is distracted from the results, then we further have to improve these results. And we are trying to bridge this uncanny valley to create something that is much better. And for doing that, we also have to look on how a human actually perceives the quality. And we are doing that currently in a new project where we use brain and EEG signals in order to have a better understanding how humans perceive virtual humans and how they actually perceive artifacts in the dynamics, but also in static images. And from that, we want to get more insights on what is disturbing for a virtual character, and then feed back that kind of information in order to improve our virtual representation. And with that, we target at least to come to a point where we actually have passed these uncanny valley and have a representation that is accepted by users. And with that, I would like to end our talk. So we have shown you different ways on how to represent humans, virtual humans, the body motion, the face motion. And here, by relying on AI techniques compared to these traditional CG approaches, we can have several benefits in terms of realism and controllability, and combine the quality of volumetric video with the ways of manipulation that we have in a CG character. So we have shown you how to do that with skeletons or with faces, where we can drive from text or speech signals and to animate these representations that have an realistic appearance. And yeah, we hope that we can see such kind of techniques also in many new applications like film, games, or e-learning. And with that, we would like to thank you all for your attention. And if there are some questions, we are happy to answer them. Thank you very much.
Thank you, Peter. Yes, Anna, I was going to invite you to come back. Welcome back. We do have a number of questions in the queue. I see a little applause emoji going up through the screen. I hope we see many, many more of those. I'd like to remind our guests that to ask questions, if you have any. As I said, we have a number of them. Oral questions will go to the top of the list. And let's see, for the first question, comes from our anonymous guest. For greater detail, can individual body parts be captured independently and then reassembled? For example, the hands and then the eyes, and then can they be reassembled, I guess, into the whole individual?
Maybe if I start here. So yes, I think that would be possible in principle, although I think you would miss a lot of details, because if you represent hands and faces individually, you lose all the connections between them, and there are a lot of deformable surface and fine details that depend on each other. And by just looking at all the parts individually, you can still learn everything, you can compose it, but you might lose all the things that have some correlation between each other. But what we are doing, we are now, Anna showed you our volumetric video studio where we captured the actors in full body resolution. So we have now a modified camera configuration where we can also replace cameras looking at detailed positions. For instance, having a detailed representation of the face or the fingers if you want. And then you can have a higher resolution on those parts, which might be more important than other parts.
Okay. Thank you very much. Next question comes from Brad. How far can you drop the resolution, while retaining acceptable quality, but such that it can be used in a lower graphic capable software or a browser, etc.?
Yeah, so we can flexibly adapt the resolution both in geometry and texture. So we start initially with very high resolution images. So our cameras are 20 megapixel video cameras. So they produce around 2 terabytes per minute as data. So very high resolution, and then we scale that down. And if we want to render, for instance, all these assets on VR glasses, so we we scale down polygonal count maybe to 20K, but also the texture information can be scaled down. But the nice approach about these hybrid representation where we have the rough model and all the texture details is that in principle, it's not a very high complexity in rendering. So rendering is fast, even on small and mobile devices. So you can do that on tablets or VR glasses or whatever.
Thank you very much. Let's see. Timur has a question. Is it possible to use photogrammetry instead of a camera rig to create an avatar?
Anna?
So what? So in my understanding, photogrammetry uses correspondences between different images. So this is actually what we're doing. We are using photogrammetric techniques in order to establish a 3-dimensional model of the humans.
Ah.
Yeah.
Or maybe the question goes into other sensors than cameras, but yes, sure, you could also use other sensors, but then you do not get this highly detailed textures.
Yeah, maybe that's the difference, because there are many volumetric video studios which use depth sensors. Maybe we didn't say that explicitly. We just have regular 2D cameras, and we use photometric methods for reconstruction.
Okay, that makes sense. I have a question, and maybe it's been resolved, but within the past couple of years, with the emergence of so many deep fakes, there have been articles written on how to tell if something is a deep fake, and one of the suggestions is to look at the eyes, and that the eyes are sometimes not quite natural. What is it about the eye? What and how does that get resolved?
Yeah, so you're right. The eyes are very difficult, and there are a lot of details and high frequency issues in there that are likely to fail. But I think that the progress in deep fakes is now has progressed so much that you don't see any artifacts anymore in the eyes of a deepfake, if it's really a good deepfakes. So this has changed a lot, and there are also public databases of deepfakes, and they appear every now and then, and often they have very clear artifacts, but they are also a couple of years old, and in AI, so 2 years is very old. So there has been a lot of progress, and I would say that it's really difficult to judge whether there is an artifact in the eyes if the fake is done very well. But we are trying to work on detectors that can find that anyhow, but it's also difficult.
Yes. I was looking at the eyes in your examples as well, and I didn't see any of the strange artifacts that you might see. But then again, I'm not an expert. So let's see. Andrew asks if the recording of this presentation will be available afterwards. Yes, it will. We'll do a little bit of editing to the video, and then it will be posted on the SMPTE website. I'm not sure if there will be an email going out, but it'll be a few days. And if you check back next week, you probably will be able to find it under the education menu. Look for webcasts, and then there'll be a button that says previous webcasts, I believe. Let's see. Our anonymous attendee. Are there any standards to define or scope such volumetric videos? He asked about SMPTE, but in general, are there any standards? And if not, how will studios massively produce content in the future, do you think?
So regarding standards, there are some standards. So we have actually standardized our body or hybrid body representation within MPEG. So in MPEG, there had been an extension for GLTF being standardized, and within that scope, so GLTF can represent virtual humans, and MPEG usually standardizes media representations. And we have used these elements and added some extensions like the mesh linking extension that allows now to combine these model representation, this animatable model representation with dynamic video textures. So we can then render content like that we have shown in a standardized way using these kind of MPEG standardization. But
Okay, so
I think it's an ongoing topic. So there are many new approaches going on, and all these nerve-like representations, they require completely new representations and different ways. I think there are not yet standards available. So this is maybe a future activity.
okay. I have one final question. This is my question, and it's okay to say you don't know, or I'd rather not answer this question, but do you envision a day far into the future where real actors and real people are no longer required? I know that's a terrible question. It's a terrible question.
It's a good question. So I think we see that in all domains that AI can replace some parts of our daily life. So currently it's mostly, we have new tools and new representations. So the human is not completely replaced. So for instance, with the techniques that we have shown today, you also need, you have to train data. So you need real actors that can produce some expressive content. And without that, it's very difficult in order to reproduce something very realistic. But of course, yes, I think that the future will change for many different professions and also for the artists and industry. So I think AI will provide challenges and also opportunities for new things that you can do. But I think at least for the next years, we still need all the humans to do something creative out of that. So I don't think that the human will disappear in any of these issues. But Anna, maybe you also.
Yeah, maybe I get these questions about the avatars quite often. Will we then be living our life in a virtual reality rather than in our real reality? But the way I see it is just it opens more opportunities for interaction that are currently not possible. So it's not in order to replace real meetings and real communication, but in order to make distant communication more immersive and open more opportunities to virtually meet and have a real immersive communication, which is important when it's not possible to personally meet.
Great. Excellent answers. Thank you so much. And I'm not an alarmist. I just thought I would ask the obvious question that I'm sure people, worry about. Well, Peter and Anna, thank you so much for an excellent presentation. I did talk it up quite a bit on LinkedIn. As many groups as I belong to, I wanted to make sure that people knew that you were going to provide so many examples and explanations of how this is accomplished, because it certainly is going to be a part of the future of media and entertainment for sure, more than it is now, and it's being used in many places. So any closing comments or any closing words that either of you would like to provide?
No, just to say thank you very much for the invitation. It was a nice opportunity to show here our current efforts and results.
Yes, thank you both for the presentation. I was very much looking forward to it, and we had a very good audience. So, thank you. And I will go ahead and close the webcast now, if that's okay. And so, thank you, Peter, Anna, for presenting. Thank you to our guests.
You're welcome.
For spending time with us. There are lots of things I'm sure you could do, but it was an honor to have you with us. Hope you found value in the webcast. And like to thank SMPTE for putting on this webcast. And close with a personal thought. Please cherish every moment you can with your family, your friends, and your loved ones. And with that, we shall end this webcast. Thank you so much. Take care, and we'll see you next time on a SMPTE webcast. Bye.